let me know when
I'm ready whenever. You can go.
Okay. All right. Hello, everyone. It is my honor today to introduce Dr. Thomas Vonder Haar, who is the 2024 recipient of the AOS Distinguished Alumni Award for Outstanding Achievement. So it's great to have you, Tom. Tom is a University Distinguished Professor Emeritus at Colorado State University, which is my alma mater, where he joined the faculty in 1970, and I was just telling Tom that I was in his very last class before he stopped teaching. It was a GPS occultation class, and it was great. I'm glad I got to take that before he retired. So Tom received his master's and PhD from our department here in AOS. He received his PhD in 1968, where he worked under the advisement of Professor Sumi. Then after he finished his PhD, he did his postdoc at SSCC. So he was here for quite a while in our building, which looks the same, by the way. And then he went off to CSU to become faculty. Tom has been instrumental in advancing the field of satellite meteorology, and this includes through involvement in numerous NASA science teams, World Climate Research Program, working groups, advisory committees. He's been in steering committees, you name it. There's a long list. Tom is also the founding director of CIRA, which is the Cooperative Institute for Research in the Atmosphere, which is located in Fort Collins, where he was director for 28 years. He's also an AMS honorary member and fellow, an AGU fellow, and a member of the National Academy of Engineering, and that's just a few of his awards and honors. So I could be here and talk about Tom for a long time, but I will turn this over to him. So thank you so much, Tom, and I look forward to seeing your talk.
Well, thank you very much, Vinny. I gathered I can hear some feedback. So can you hear me in the back of the room? Okay. Well, I'll tell you, of all the, you get honors, if you live long enough, you get a lot of honors, but this one means as much as any other. I mean, right up there. Because you do spend a good part of your life as a student and postdoc. I stayed here a couple extra years in the Space Science Center. And left here in 1970. So some people I remember, and some new ones I've met along the way. I've been back a few times for both either the department or the SSCC anniversaries. And so again, we'll talk about, this is not a deep science talk at all, it's a talk about an alumni who has a lot of memories, but we'll follow a particular thread here, what I call the Wisconsin thread, in with radiation budget leadership and actually science analysis of data and things. It stretches back into the 50s, actually. We didn't have satellites until the late 50s, but we'll see that Professor Letow, who was a professor, and on my graduate committee, he was here. He'd done a paper in the 50s on Earth radiation budget. So while Professor Sumi is the one who created the first measurements from satellites, and we'll talk about those. And we'll touch on people along the way. But I really won't have time today to talk much about Hank Rivercomb's work. He did work with both Herbos and now with Clario, right? Are you still working, Mr. Clario? Clario's still on our priority list. And Tristan, of course, will give you all the news about the latest pre-fire data. But I wanted to put him on here because Wisconsin thread is still going on. Okay. This is, sometimes I give this talk or parts of it to a really non-technical audience, so I always like to show them a picture of Earth, and I'd like to point out that there's a lot of energy in the Earth system, the oceans and the atmospheres, and some of you are working on all the parts of this already, forward transports of energy, the petawatts are involved. And sometimes when people come up with a new idea of modifying the atmosphere in some way for good purposes, I remind them of all the energy in the atmosphere and how it takes, and how puny humans are in comparison to that. There have been several periods in my lifetime of excitement over weather modification of some kind. I think we're in another one now, but I'm not going to get too involved. There's Professor Vonder Suomi, PhD in Chicago. He's a member of the Emeritus Hall of Fame, many honors. The self-admitted tinkerer. There's a book about it as a biography in your library that some of us collaborated, Paul Menzel and Gene Phillips collaborated. There's an article in BAMS magazine if you want more history about Verne. But this is not all about Verne. I'm talking about kind of a thread of research that keeps on going. Oh, there I am, but I wasn't really there. That's the Explorer 7 satellite. That was the first satellite, and Suomi's two instruments are, Suomi and Bob Parent, the electrical engineering professor, his colleague, were able to put, after several struggles with earlier satellites. Now remember, back in the late 50s, there was an International Geophysical Year going on, and part of the U.S. contribution was this satellite idea that Suomi had. There were some other scientists in the States, and even worldwide in the Soviet Union, there were scientists who wanted to measure the Earth's radiation budget. But Suomi and Parent were able to do it on Explorer 7, 41.5 kilograms. There have been numerous attempts to launch a science satellite. There have been one success called Vanguard. It was a much smaller satellite. This one carried Van Allen's radiation experiments and Suomi's black and white radiometers. These were there's stories in his biography about how they came to be little hemispheres mounted on mirrors. But the whole idea is to have, we'll talk about it in a bit here, measuring all the reflected and emitted outgoing radiation. So one of the anniversaries, Jerry Denberger, one of my generation graduates, he worked with Reed Bryson. Jerry took this picture. We were down browsing in the library here. But that was the 3/4 size. And then, another anniversary, we actually showed the group, I think this was an SSEC anniversary. We had it down at the Monona Center, and probably Hank organized it or something. But what we had were some printouts, some paper printouts of Explorer 7 data that a graduate student had saved. He got his PhD, Fred House, and he had saved them all these years, a stack of paper printouts. And it was just a list of the latitude, longitude, and the time, and the measurements from these black and white sensors. Well, Paul Menzel, who gets credit for this, I saw him briefly this morning, he and some of his colleagues took these printouts and put them into a modern display system. So you got 1959 data displayed in 2005 or whatever, something like that. But you can see the field of view of the instrument, which is shown here, was basically horizon to horizon. And you can, if you look carefully, you can see the orbit's not circular because it's farther away from Earth over the United States. It's closer here. See but we were able to measure Suomi, and he had one student, an Air Force student named Melvin Weinstein, who published a paper in the bulletin of the Month of Weather Review. And in those days, it was probably one of the first meteorological satellite. They did an analysis kind of like this, laboriously by hand over the Pacific Ocean and compared it with the different weather patterns. So essentially, this was a proof of concept experiment, and it proved that Suomi's Parent's idea would make measurements. The orbit was kind of erratic. The readout stations were off and on, the tape recorder tried to record data between readout stations. Anyhow, it's a long story, but we didn't get very much data, but it was a good proof of concept. So SUMI then, with the help of colleagues that was in the U.S. Weather Bureau and in NASA, was able to see the red arrows pointing to, if you look closely there, you can see black and white hemispheres on circular mirrors now. And they were on booms to keep them away from the heat that would flow from the satellite, which was noise for measuring the energy coming from the Earth. And you can see Taro's principal instrument was this Vidicon camera here. Sometimes they actually fly too. But the challenge here was that we had to go in the orbits that it could launch Taros out of Cape Canaveral in those days. So we only had inclined orbits that were like 40 degrees or 45 or 50 degrees. So we really didn't get the global data we wanted. And again, the big failure item in those days, if the rocket didn't blow up on the launch pad, the big failure were the tape recorders. So he told me he just borrowed James Van Allen's tape recorder that he developed over at the University of Iowa, so that's a good example of sharing at the time, and it was the best available at the time. So we got some months worth of data from these satellites, and it was very much advanced beyond the Explorer 7. But we really wanted to fly, and everybody here like Hank and David and other people who know radio transfer, you really want to fly a flat detector. You want to detect, we're flying below the Earth, we want to detect all the radiation coming through a spot at satellite altitude. So SUMI had balloon-borne instruments that were flat plate detectors that measured radiation fluxes through the atmosphere at night. So he never wanted to fly spheres or hemispheres. In fact, he was really concerned when a very good scientist from England wrote a paper criticizing him for flying these non-flat things. But he had to go to those detectors because the early satellites were wobbling and flying in uncontrolled, they weren't Earth-oriented. It turned out we flew this, I say we because now I'm on the team with Bob Parent, and these black and white radiometers were flown on Air Force satellites. We had some, well, I think this makes sense, but the black sensor would see the solar, terrestrial, and reflected radiation, while the white sensor would see the terrestrial. It would reflect as best we could make one, would reflect the solar radiation and just measure the infrared. But the good news was we got a chance to piggyback these flat plates on an Air Force satellite. The Air Force meteorological program started hold back, again, we're in the mid-1960s. At that time, they were taking pictures of things they wanted to take pictures of, and they didn't tell anybody about it, but we were able to help them. So Vern, Sumi, and Bob Parent and I would go to Omaha, Nebraska, and help them. And in return, they let us put the black and white flat plates on the diameter of these satellites. And that gave us, they launched into, this is supposed to be a sun-synchronous orbit, we just kind of ginned it up. They, in the near polar orbit, so with a wide field of view, we actually got polar to polar measurements of Earth radiation. So we got the first global values in like 64 or 65 at that time. Like a lot of the students who were talking at lunch today, you sometimes have a couple of dissertation topics, you're kind of weighing which one should you go with. But when we got the global data, I made up my mind completely. I worked for analyzing these data. One of our challenges was we could measure the reflected solar radiation from Earth, but we didn't know how much was coming in from the sun. There are all sorts of people who have made observations of what's called the total solar radiance, they did it from high altitude balloons, from mountaintop observatories. But it turned out we didn't have to know the absolute value, we just wanted to know the ratio of the reflected energy to the incident energy. That gives us the albedo. So Sumi would show this picture or a picture like it and say, oh, it's simple. We've got 3 equations and 3 unknowns. And then it was Vonder Haar figure out how to do that. Well, we had, every time we crossed the terminator, we had these measurements, that A, B, and C, and I won't read all that. But with those 3 measurements, 28 times a day we crossed the terminator, we were able to be confident that we're measuring the reflected solar energy, as well as could be done with these instruments at that time. And so still, again, we're in this 1960s now. There were many different estimates of the total solar irradiance, and debate on whether it varied and why it varied and things. So we'll come to that in a little bit. So to get the real Earth radiation budget story, there's still a missing link here. But comparing to the pre-satellite estimates, mostly done for the Northern Hemisphere, I mean completely done for the Northern Hemisphere with climatological data, here you see Professor Letow published in '54. I'm not sure if he was here at the time. He might have been. But it was published in a German publication. Professor London at New York University had taken all the climatological data from World War II, all the ships and planes, and by this time people had gathered that data set. A few good things that came out of that war, but they had made estimates of the albedo, and they were a little high. And you can see they started off quite high, and mostly that was because people didn't know the albedo of clouds, they didn't know the distribution of clouds, and as Andy and others know, we're still measuring now the global variation of cloud cover. So it turns out that 1% albedo, when you think of all the energy coming in from the sun, that's a lot of watts per meter squared. So this gave us some new data set that we plotted and compared. The dotted lines were the pre-satellite data, the best estimate from Professor London. They were only for the Northern Hemisphere. Nobody knew even how to estimate the Southern Hemisphere because of lack of data. But what we found was, and we plotted also some later Nimbus data on this chart, I'll talk about that later. But we found that the Earth was darker and warmer than previously thought. And this had some people asking questions to Sumi and I both. That would get calls, are you sure your data is okay? Did you do that twice? And we said, yes, we checked it. We told them about calibrating against the sun, because the black paint and the white anodized aluminum definitely, most certainly changed in orbit due to exposure to solar ultraviolet. But we didn't know, we didn't need to know the absolute absorption, we just got the ratio of the stick at the albedo. And then nighttime infrared was much simpler. Gave us another check. So this is what we reported in our papers, that more energy had to be, because of the tropical regions were especially overestimated in their albedo. More energy had to be transmitted poleward. Well, again, that got into another exciting adventure where we worked with Abraham Ort at GFDL, who had good atmospheric data, and he and I worked together. And if we had the total net radiation from the satellites, and he had the atmospheric V dot del Q and V dot del T, the enthalpy and the moist static energy transport, if we subtracted them, we would estimate the big air bars, the ocean transport. Well, this got the oceanographers all excited because they didn't believe the ocean transported that much energy, and I had calls again, hey, Vonder Haar, let's go back and check your numbers again. It turned out that a lot more work has been done in the intervening years. This actually, this little figure came out of Dennis Hartman's climatology books out of 1994, so we're still seeing some history here. But the oceanographers are now, and I think people like Kevin Trenberth and others who have spent a lot of time analyzing atmospheric data, find that there's probably less ocean transport than we show here, but certainly a lot more than the oceanographers expected. And there's more atmospheric transport than Ort and colleagues at GFTL had gleaned from available Raven sondes and things, because the Raven sondes weren't measuring globally the absolute humidity very well, and especially in the upper troposphere. So there's actually the corrected figures today of this. You can find them in the literature, and they'll show greater atmospheric transport and a little bit less ocean. But it was pretty exciting to publish in the Journal of Physical Oceanography, because I knew absolutely nothing about the ocean. I still don't know much. But one of my colleagues, Wade Schubert, at Dynamicist at CSU, was reading the collected works of Henry Stommel, whom some of you will recognize. And in there, he had a little footnote, a little note saying how happy the oceanographers, some of them were, that the ocean was transporting more energy, and they had a big role in the climate program. So that made some people happy. Okay, we did get some very smooth maps of the albedo from those flat plate radiometers, and some things of interest. We've got that planetary albedo of 29% plus or minus 1 or so. But the polar regions were a little different and had been thought. People thought, really had no estimates of the energy reflected and emitted from the Antarctic until that International Geophysical Year, where there were a lot of observations taken in the South Polar region, including Bloomborne observations, which we could compare our satellite data from the 60s with some nighttime infrared radiation measured from balloons into the stratosphere, at least, because they carried Sumi's flat plate balloon-borne radiometers at that time. So, but then on the albedo side, it turned out Antarctica averaged greater than 60%, but the North Polar regions, I didn't put it on there, were down around 40–50%. So they were, at this time, people thought the Antarctic and the Arctic were much the same. But we now know there's a lot more melting and puddling and things in the north, even if the cloud cover isn't there. So we did get things. The Sahara Desert, and this was noticed by one of my grad student colleagues, Fred House. He had 4 months of data, and he looked at the Sahara, and it's losing more energy in a 4-month period than it's gaining. It's hot and emits a lot, and it's pretty highly reflective. And that got Jules Charney very excited. Most of you know the name Jules Charney. He liked to look at observations. He was thinking about the theories of why deserts grow or shrink, and he seized upon these data and another picture I'll show you later on to support his theories of desertification, growing deserts. Because if you lose more energy than you gain, and you don't cool off, which it doesn't, and the energy's got to come from somewhere, and that was subsidence. And subsidence then brings aerosols and things, which involves more kind of a positive feedback to the radiation situation. So, still, the question, could these results be true? And the community, international community, and the U.S. and everyone said, yeah, we better check these early measurements. By now we're into the Nimbus period. And as Nimbus quickly, now Nimbus was a much different satellite than the early ones that we were flying on. Nimbus used a lot of new engineering technology. It had a payload bay that could carry a lot more power with the solar panels. It was Earth-oriented. You could put a scanning radiometer of the kind we even still use today, and it would be Earth locatable. And NASA was actually planning this to be what then was called the National Meteorological Satellite. So we built this wonderful Nimbus satellite. They flew it 7 times for research, and NOAA could not afford to buy it for operational purposes. Instead, NOAA bought that little Air Force satellite that I showed you, that little 50 kilogram air, and made that their first operational, they called them the ESA satellites. That's too bad, but it didn't go to waste, because this design, NASA used it for the Landsats. Some of you know about Landsats and Earth Resources satellites. Used the same thing. Okay, so a little story about Nimbus. So that went on. Well, we flew Earth radiation budget experiments, and I have to mention Bill Smith Sr. Bill Smith and I were grad students together. Bill did some great things. You guys all know him here. He's a professor here. He's one of the famous alumni. Bill and I actually went to undergraduate college at undergraduate school at St. Louis University together. When I first came to Madison, Bill Smith was driving a car. So Bill goes back a long time. He was the PI for a Nimbus 6 radiation experiment. And I'm showing you data from Nimbus 7. Nimbus 6 was like one of these, things are happening so fast, we didn't have enough people to analyze the data. And the engineers were already ready to jump on now to the next best satellite. And sometimes you run into this with field programs, and you say, wait a minute, don't launch Nimbus 7. I haven't analyzed Nimbus 6 data. I know exactly what happened. But Nimbus 6, again, was kind of the pioneer. They had thermopile detectors. They were different detectors, but they had both scanners and wide field of view. But what did it do? It gave us continuous data records for, in this case, about 8 or 9 years. Well, one of my PhD students, David Randall, analyzed this. Now, first thing you're seeing, this is the net radiation. Notice the scale. Oops, notice the scale. It's positive downward. That means energy gained by Earth. This is energy lost by Earth. And these numbers, again, were calibrated as best we could. And a good team of people who did the calibration. And you can see some interannual variability, but mostly you see when we're closer to the sun, we get more solar energy, and that drives the positive, which is the values down here, the positive values. And when we're further away from the sun, we're losing more energy. So a lot of the data you see today, they take out this annual variation, but I think we have to pay attention to that as well, because it's a pulse on the Earth's energy system that models probably can help us understand. We got a lot higher resolution data from the scanner, and so the Sahara Desert, in this case I'm showing the long-wave radiation because I showed this at one of the pre-fire meetings that Tristan invited me to in Colorado. I wasn't looking. This is the outgoing long-wave radiation. You can see the more detail, kind of a high value of outgoing radiation over the Sahara. But the thing I was, since pre-fire, I was looking at the far infrared, and they'll be getting much better measurements. I'll just say that here's what we found from, this is a period of time in the summer, our summer, their winter. and contrasted the outgoing radiations. Over the polar regions, we're going to learn a lot more about from pre-fire. Okay, well, we didn't know, if you don't mind, I'm going to sit down a little bit because old alumni are allowed to do that. Okay, we didn't know, for solar physicists and astronomers have known that the sun had a cycle, monthly sunspot number shown at the bottom. And people speculated that the sun did or did not respond to those energetic activities in the magnetic fields and stuff in the sun. So the ERB experiment, ERB, on Nimbus 7 had a small electrical substitution radiometer about the size of my thumb. There was a little cavity that was black painted, and it was one of the best radiometers we had. This was back in the late 70s. And so this was, if you look at this chart, put together by Peter, well, great cop at last, but given to me, I think, by Peter Polewski. If you look at this, you'll see, the first thing you should look at is the scale on the left. And I put in here, that is 1,000 parts per million, a tenth of a percent. So while these look like big differences, they're really quite small compared to the total value. Today we know, this is a whole lecture itself, and some of you have probably heard it, with better radiometers and over several decades, we now know that the actual value is estimated to be 1361. I could have used that back in my dissertation, but it would have been, that came into my defense of my dissertation because there's a lot of students here, and I had the Earth measurements, I had the Earth gaining 5 watts per meter squared. And the first question asked by Professor Letow was, Vonder Haar, how could that be? What is wrong with your measurements? I worked on it for 3 years or so, and he was asking a good question. Well, the answer was, I had used an estimated value of the solar constant that was, oh boy, I used to remember that was way up here. So, wow, but I didn't know it at the time. So now, as instrumentation got better and better, and especially designed, cavity radiometers or electrical substitution radiometers, we're still continuing this measurement now. But we do need, it's never guaranteed in this business that we'll keep measuring the sun. It's really a stay here. I took a long time on that slide, so let's see the time. Okay, you better give me a warning when you go on all day. Okay, this Nimbus was really a gold mine of experiments with these 7 satellites. On Nimbus 3, Bill Smith and David Wark were getting the first infrared temperature soundings and demonstrating them to the weather people that they were useful in forecasting. So all this back in this early 70s time period. But there was a interferometer flown, and Hank knows a lot about these. But Rudy Honnold at NASA Goddard and his team flew an infrared interferometer, and I brought this out. Again, to show Tristan's people, because Tristan and the pre-fire guys are making measurements making measurements way back in here, this water vapor band and all this region out here, not shown by Honnold. But again, showing us suddenly we went from very crude instruments that were flying on satellites that were likely to end up in the Atlantic Ocean, and in less than a decade we were flying some pretty sophisticated weather instruments and climate things, and things just got better. ATS, geostationary satellite, that launched in the late 60s, and better instruments going on to that too. Again, I'm going to skip one slide because Tristan can tell you more about that. One of my students actually looked at some of these data as a function of latitude. Was able to see the effect of gases, and he tried to take the clouds out of his picture to get just the gases. I don't know how successful we were. We only had about a month's worth of data, but we still needed better observations. We had Nimbus. Nimbus agreed with the early swingy radiometers, and so NASA sent out a call for proposals for a new Earth radiation budget. And once again, Wisconsin applied. Sumi and Hank, what was it, Urbos? They had a great instrument. I liked it. I worked with Paul, and I designed a simple instrument. But I mean, actually, I liked the Wisconsin one better. But NOAA had one, and Langley had one. It was a great instrument incubator kind of competition, and
I think they took part of yours and part of ours and had Langley build it.
I think they did. And Langley actually shipped it to what was in TRW, I think, built it. It got kind of a little weird, but at least we got what the scientists wanted. We wanted to get a better estimate than had been done even from Nimbus. There was some calibration questions and things. So I showed it to you in the shuttle bay. How many of you have ever seen a shuttle now that you've been down on Earth? Okay, they're about the size of the bay is about the size of a school bus. You can see them at the National Space Center out at Dulles Airport and a few other places. So this satellite it turned out that we were on a roll, so we told NASA we needed more than one. We needed 3, so we ran some computer simulations, and we found that to get the diurnal variation, which is still an open question of the energy going out to space, we all know about diurnal variations, we needed 3 of them. One of them launched from a shuttle called ERVS that year. It was in a 57-degree inclination orbit, which is about as far as high latitude as you can get with a shuttle launch, if you don't have an extra rocket. Then Dave Johnson, who was running NESDIS, which is in those days the Meteorological Satellite Laboratory, it might have been ESA or something, but Dave Johnson said he had a new satellite. Now, NOAA had some money. They gave him money to have a bigger satellite, but he had extra room on it. So we made a deal with Dave, who's a good friend of Vern Sumi's, and said, if NASA will build 2 more instruments, will you fly them? He said, sure, but don't ask me to analyze any data or anything. Just give it to NASA, and they did. So we ended up with a little constellation. And the first one, the shuttle launch there, was done in October of 1984. And I was the PI of this system, and I was sitting down at the Cape chewing my fingernails, and Sally Ride and Kathy Sullivan were the 2 mission specialists, and they had to operate the Canadian arm there to take the satellite out of the bay. There's a trunnion point over here, I think. So they would hook it on, and they put it out. This is a radar that never, the other thing in the bay here is a radar that never left the shuttle. It just turned it upside down and they were looking at the Earth. This guy was the first science satellite launched from the shuttle. And so it got launched, and it joined 2 others. They didn't all get launched at the same time, but we had a mini constellation. Today, you look up, and there are a lot of constellations of satellites. And when the data started coming in, this was processed by Lee Kyle and the science team. They had a science team for this. And it turned out that the early results agreed with Nimbus, and Nimbus agreed with the early radiometric data. So at this time, we had 3 satellite experiments, got pretty much the same global and zonal averages. And that's what we need for a scientific method, right? Independent reproducibility of results. These are different instruments, but they still measured that lower albedo and 40% more required poleward energy transport. So that allows a lot, and now we need to go further into deeper studies of what happens in the atmosphere with clouds and radiation, heating, cooling, what happens at the surface, things of that kind. Well, we also need to look at long-term and interannual variations. So here's Langley, the group at Langley who was analyzing the data from IRBI. You can read it. I have a little nimbus on here. This is a 20-degree north and south latitude zone, which is an area of special interest because of that lower albedo. This actually is outgoing long-wave radiation, but Bruce Willicke and others published this data. And you see the continuity. And now this has been continued with the series instruments. But Hank, they took off the electrical substitution radiometer. And I don't know why. They didn't ask me. That was the best radiometer on board. They took it off, and they have good scanning radiometers and 20 years of data, which have uncertainty estimates that are complicated because they use a lot of assumptions. But nevertheless, you're able to pick up anomalies. Again, I'm looking back at Nimbus now. There was a nice ENSO in 1983. Yeah, 1983. And so we did, one of my students, David Randall, did this, looked at Nimbus, and you'll notice these are the standard deviations of that 8-year period of net radiation, and deseasonalized. So we took out the Earth's orbit, the non-circular orbit, and we found that during this ENSO, during this period, the ENSO shows out here as a large variation in that 8-year period caused by the ENSO here and here. But we also found this strange, highly variable radiation region in the Gulf of Guinea. And it wasn't understood by us. We looked at some cloud data. We saw some different clouds there. There's a lot of biomass burning up in Africa. So my point out this slide is there's a lot of gold still left in the mines of the old data. So if a student wants to work on data from 1970s or 80s, it never was fully analyzed by anybody. The data are preserved, carefully curated in the National Space Science Data Center. And I get emails from young data curators who say, what was that third column in the data on Nimbus? And I said, boy, I don't remember. But there is a lot of good data there. Because one of our young scientists today, Jake Christie, who's on the Peter Paluski's Libera science team, I showed this slide in the top to him. So he went and took a similar period of data from the current radiation budget sensor series in 2009, 2017. There was an ENSO in this period also. There was an ENSO, but we all know by now that an ENSO is not an ENSO is not an ENSO. These oscillations are variable. They have some fundamental similarities, but in this case, Jake said, okay, we got an ENSO, it's here. Change the clouds here, and maybe it did something here. What it did here off the coast, I don't know yet. Maybe somebody studied that. Well, look here, Gulf of Guinea, in a similar period, no special really outstanding variation. So there's still things to study in these areas. Oh, and of course, one of my Japanese colleagues sent this to me from one of the textbooks. The point being, I showed this at SSCC's 50th anniversary because, you know, the things that you guys are doing here in Wisconsin are definitely being used around the world. And there are a lot of people around the world now interested in more measurements of the Earth radiation budget. So, about 2 years ago, I gave a paper. They asked me to give a paper, and I said, I don't want to give a paper. I want to give a poster because I can stand there for 2 hours and talk. And if you ask me to do a paper, I get to answer one question. So I did this poster, Peter Polisky and I, and it's in the recording if you want to look at it. It's published in the GWEX Quarterly. It's a publication of the Global Energy and Water Cycle Experiment of the World Climate Research Program that some of you will be involved with. I know Peter and Tristan is. But we said, okay, here's a history. We've got a lot of science. What's going to continue? Well, what's going to continue is this Libera mission that NASA has funded, and it's going to fly in about a year or two. Whenever they launch JPSS 4. They were planning for 3, and 3's in storage, and it's easier to hook this instrument on, and they're going to launch 4, I believe, before 3. And on that will be the Libera instrument, which has some outstanding new characteristics, which I hope Peter has been out here to give you a seminar. If he hasn't, we might want to invite him sometime. But the Libera arrow, we call it. See, I've talked to you about this slide. I've talked this much. And then there's more that's been done on the Earth Energy Imbalance. So it goes back to Professor Letow's question in 1967. You know, what's this imbalance and what does it mean? And how people with some ocean data are compared to the measurements at the top of the atmosphere. There's a lot of research there. But the Libera is the only continuation we have. But it has the outstanding characteristics of these new vertically aligned carbon nanotube black detectors. So I keep picking on Hag, but they're being used for black bodies and a lot of things. If you take, they're built at the National NIST, National Institute of Standards and Technology. They're just a very, very black surface that absorbs all the light that we are interested in, all the wavelengths, like 99.9%. And so this Libera will be a scanning radiometer, not unlike the ones we have today, but the detectors will have these very black surfaces which have already been flown in space to measure the total solar radiance. So they survive launch. But my understanding is you take a piece of pure carbon, a small piece, put it under high temperature and pressure, it starts growing these crystals. And I've seen them, and if you look at them, they look like a black hairbrush. Does that analogy work for you? You look at a black hairbrush, you don't see much but black. And of course, so we started with these painted black detectors, and Sugi found this paint called, made somewhere in Wisconsin actually. It was a special paint, flat black. We used that. And then there's been a variety of instruments, technology through this. In about a year and a half or 2 years, the Libera instrument will make much more absolute values. And we have to keep measuring the total solar irradiance because our sun is a kind of a variable star. So what the younger generation, not me, but the younger generation is now trying to work internationally to have what's called an Earth Radiation Budget Consortium. And it's kind of like ISCA. It's get nations together who want to participate, let's all contribute, and let's fly like Those of you who took our satellite class at CSU, you know Stan Kidder has an orbit program, and you had to do problems in orbits. And it turns out that if you take the operational weather satellites that are flying today and add just a couple more small satellites, you could get the diurnal variation. So there's a future that the next generation, Tristan, Jake Christie, Maria Hakuba, they welcome people to become involved in the future after Libra, which will launch, say, in 27 and last 7 years. So we hope to keep the record going. That's all I have. Thank you very much. Oh, I forgot my last slide. I've got to do this last one. Hank sent me this one too. Well, I'm glad you're here, Hank. You made my thing. There's a picture of Libra. There's the orbits. There's those guys. That's the problem. We haven't even done the atmosphere. David Henderson, a lot of people working on this. But there are no boundaries in education. This is from your satellite going to me. I took this off of video. Bill Smith and I and Bob Fox and a whole lot of people were sitting around a table. They were videotaping it. I guess Gene Phillips did that. And 10 years later, I get a call from the Alumni Association saying, can we use this thing that you said? And I said, what did I say? He said, I was talking about how much we learn outside the classroom. Of course, you learn a lot in the classroom. But, I mean, especially with Sumi, his classroom were kind of the latest idea he had the day before, and he puts it on the board. But learned so much outside the classroom. Good department like here. I'm just so happy I was able to come through the program. Thank you.
As usual, we'll start with any students that might have any questions.
I asked a lot of questions at lunch.
Yep, that's fair. Right, yeah, we'll go ahead and open it to everyone.
It's open now. Yeah, I have a question. So when I was a grad student 10 years ago, one thing that I kept hearing from people at Nestis and other experts in satellite remote sensing was that we were at the peak of the satellite era and the golden years and all of that, and it seemed that they were trying to tell us that we were in decline. I hope that I know that that's not true, but how do you see the future of the field right now from your perspective, and what would be the advice that you give to us as the next generation of scientists in remote sensing in terms of what type of missions we should follow?
Well, I think there's been several peaks in my lifetime. I expect there'll be others. But I think we're heading toward a peak with all the what they call distributed satellite systems, where you get more launch opportunities to go into different orbits and fly, and the technology to fly smaller instruments that not so costly. You don't need these bigger rockets like Free Fire, example. So I think we're heading for another peak. I think it's a bullish time. I'd like to be a grad student again. And I think there are going to be opportunities, not just from NOAA or NASA, but from international consortia, but from private sector people. You've heard of methane sat, pretty much privately funded. I think we should encourage private sectors to join these consortia. It's not just universities. It could be put some money into them. I could see. I haven't run into. I was on a committee. We've all been on committees with Quinn Shotwell, who's the chief executive officer of SpaceX, and I think not me, but the next generation, if they have some good ideas, they should go down to Texas and talk to Gwen and say, how about a couple free launches from SpaceX? You guys ought to do something green instead of just collect people's voice transmissions or whatever. I think they might say yes. And I don't think we have to do everything with no asset government money. So I think we're heading for a peak. A lot of opportunities. I'll probably be a valet after that. Not so bad. I mean, it's really been great. The sea pre-fire was really a good demonstration. Sure, Andy.
Tom, yeah, so do you think we'll ever, I know there's a kind of a debate that we may not need to continue these broadband flux measurements and that our hyperspectral sounders and our other, more and more shortwave measurements. Do you think that, are you in the camp that we really do need always to carry on these broadband?
Well, as long as they don't add to the expense, and they certainly don't. They're an excellent, check. The Nimbus 7 science team had both wide field of view and that's probably the best. And then URBI example. And like if we're having problems with calibration of a shortwave scanner or something because of mirrors or whatever, we actually, looked at the wide field of view, used it to assist with the in-flight problems with the scanner, and kind of were able to then look at the nighttime data, wide field and scanner, and be more assured of things. I think I'd recommend it as long as it didn't break the budget. And I don't think it will. The Europeans, I think, on EarthCare have a broadband radiometer. It's not totally wide field. But it's fairly wide, isn't it?
I think so.
Yeah. But, the technology today, flying stuff that you could build in the lab here, that the advantages of getting them on smaller satellites and stuff, I'd advocate for it. Now, you'd have to tell me what you want to fly for clouds. That's different. I'll talk to you tomorrow.
Sure.
Thanks again. I appreciate being here. Thanks.